Welcome to the System Design Framework channel, where we simplify complex system designs and turn them into easy-to-follow step-by-step guides. In the previous video, we took a deep dive into the system's key APIs, the tools that power interactions and connect the entire platform seamlessly. These APIs act as the communication bridge between users and the system. They're the essential building blocks that make everything run efficiently and effectively. If you missed that video, no problem. You can find the link to it and other videos right in the description below. Let's talk about the databases and schemas that form the foundation of a social media platform. These are carefully designed to handle all the essential use cases, things like user registration, content creation, social interactions, privacy management, and more. Different types of databases, such as relational, NoSQL, and key-value stores, have been chosen based on the nature of the data. Let's talk about user registration and profile setup in a system. So, when a user signs up, we need to store their authentication details, right? Things like usernames, email addresses, and most importantly, hashed passwords. Now, to handle this type of structured data, relational databases like PostgreSQL or MySQL are fantastic. They offer a great way to maintain data integrity and ensure everything stays organized. On the other hand, when it comes to user profiles, the data can be more flexible and evolve over time. That's where NoSQL databases like MongoDB shine. They're great for storing things like BIOS, profile pictures, and other personalized details that might vary from user to user. Let's break down the schema for these tables. First, we've got the user table, which includes a primary key to uniquely identify each user, the name they'll use to log in or be recognized by, user email for communication and recovery purposes, password hash, because we never store plain text passwords, and timestamps, created at and updated at, to track when the account was created or modified. Now for the profile table, which is linked to the user table, another unique primary key, user ID, that acts as a foreign key to tie the profile back to the user, a bio text field for that personal touch, profile picture URL, to store the location of their profile image, date of birth and location, for demographic or personalization purposes, and of course, an updated at timestamp. With these two tables, we can effectively manage both authentication and profile information in a scalable way. It's a solid foundation for any application that needs user accounts. Alright, now let's dive into managing post content. The stuff users share like text, images, and videos. When we think about storing this kind of data, a NoSQL database like MongoDB or Cassandra is an excellent choice. Why? Well, these databases offer a flexible schema design, which is perfect because the structure of posts can vary. Plus, they handle fast read and write operations, which is essential for smooth content creation and user experience. Let's take a closer look at the schema for a post table, a unique identifier for each post, a foreign key to connect the post to the user who created it, the main body of the post, which could be text or a mix of text and media. If the post includes an image, this is where we store its location. Similarly, if there's a video, this field points to it. Created at, to record when the post was first shared, updated at, to track edits or updates. This setup gives us a clean and efficient way to manage posts, whether users are sharing simple text updates or rich multimedia content. It's also highly scalable, which is key as the number of posts grows. Alright, let's dive into likes and comments on posts, the core of user engagement in any social platform. Likes and comments are what we call social actions. They're tied directly to posts and give users a way to interact and share their opinions. To manage this kind of interaction data effectively, relational databases like PostgreSQL are an excellent choice. They make querying and analyzing these engagements a breeze. First up, the likes table, a primary key to uniquely identify each like, a foreign key that links the like to the specific post. Another foreign key to track which user liked the post, and of course, created at timestamp to capture when the like happened. Next, we have the comments table, the primary key for each comment, linking the comment to its corresponding post, user ID, to track who left the comment, where the actual comment text is stored, and just like the likes, created at timestamp when the comment was made. This setup is efficient, scalable, and makes it easy to add new features like comment replies or reactions later. Let's dive into sending direct messages between users. When we talk about messaging, the key here is fast and efficient real-time communication. For that, a tool like Redis is fantastic. Redis works as a key-value store, and it's great for handling messaging queues or short-lived messages, perfect for real-time performance. But what about storing those messages for the long term, like keeping conversation histories? That's where MongoDB comes in. It's ideal for this because it can handle the kind of unstructured or semi-structured data that messages often include. Now let's break down a simple schema for storing messages. In the messages collection, we'll have a unique identifier for each message, foreign keys to identify who sent and received the message, the actual text of the message, what the sender wants to say, and finally, sent at timestamp to record when the message was sent. By combining Redis for real-time delivery and MongoDB for storing message histories, you get a system that's both speedy and reliable. Alright, let's dive into the concept of following and unfollowing users, a key feature in any social platform. This interaction is all about managing relationships between users, and it's something a relational database handles really well. Why? Because it lets us store these relationships in a way that's both structured and efficient for things like generating a user's feed. The magic happens in a follow table, and here's what that looks like: a primary key to uniquely identify each follow relationship, a foreign key that represents the user doing the following, another foreign key, this one pointing to the user being followed, and followed at timestamp to track when the follow action happened. With this setup, it's super easy to look up who a user is following, or who's following them. Plus, when it's time to generate a feed, you can quickly fetch content from all the users someone follows. And when they decide to unfollow someone, just remove the corresponding entry from the table. Simple and clean. When a user wants to update their profile, maybe they're changing their bio, location, or profile picture, we need a system in place to handle those changes efficiently. Relational databases work really well here, especially because they let us track updates alongside timestamps. It helps to keep a clear history of what's been changed and when. Now, for profiles with more dynamic or flexible fields, MongoDB can also be a great option. It's designed to handle evolving data without requiring strict schemas, making it perfect for diverse profile updates. Here's how we can structure a profile updates table to log these changes: a primary key, uniquely identifying each update, a foreign key that ties the update to a specific user, a field name that tells us what was changed, like bio or location, old value and new value, to keep track of the previous value and the new one. This is super helpful for audits or rollback scenarios. And finally, updated at timestamp to record when the update was made. By structuring updates this way, we can ensure data integrity and make it easier to debug or trace user actions. Plus, having a log of changes adds transparency to the system. Next, managing privacy settings, something super important for any application that values user control. Privacy settings let users decide things like who can see their posts, who can send them messages, and who's allowed to follow them. To make these settings fast and efficient, we can use a key-value database. Why? Because key-value stores are excellent for quick lookups and making changes to individual preferences. Perfect for something like privacy settings. Here's how the schema might look for our privacy settings table: a primary key to uniquely identify each setting, a foreign key that ties these settings to a specific user, describing what the setting controls, like post visibility or message permissions, store the user's preference, like friends only or public, and update it at timestamp to track when the user last changed this setting. With this setup, any changes users make to their privacy preferences can be applied quickly and efficiently. Plus, it's scalable, whether you've got 10 users or 10 million. Moving on to sending friend requests, a key feature in many social apps. When someone sends a friend request, we need to store that interaction somewhere and keep track of its status. This can be easily managed using a relational database. Why? Because relational databases are great for structured relationships like these. We'll use a friend request table to store the details of each request. The schema would include a primary key to uniquely identify every friend request, a foreign key that points to the user who sent the request, another foreign key for the user receiving the request, tracking the progress of the request. It might start as pending and then change to accepted or declined depending on what happens, and finally, sent at, timestamp to record when the request was made. This table gives us a clear and efficient way to handle friend requests, track their status, and ensure everything is logged properly. It's straightforward but super effective for building a feature that users rely on to connect with others. Let's dive into how we can handle content reports in a system. When a user reports something, whether it's a post, comment, or another type of content, we need a way to store and track that report for moderation purposes. A relational database is perfect for this because it allows us to neatly link the report to both the user and the content being flagged. Plus, it lets us easily track the status of each report, which is essential for resolving disputes. Here's a quick breakdown of the schema for our report table: a primary key, uniquely identifying each report, a foreign key linking the report to the user who submitted it, another foreign key, this one pointing to the piece of content being reported. Store the type of report, like spam, abusive, or misleading, whether the report is under review or has been resolved, and of course, a created at timestamp to log when the report was filed. With this setup, moderators can easily track reports, follow up on disputes, and keep the platform safe for everyone. It's clean, efficient, and gets the job done. Finally, when a user logs out, we need to remove any session information that's stored, either on the server or the client side. This ensures that once they're logged out, they can't access any protected areas without logging in again. Now, to manage sessions effectively, we often use Redis or another fast key value store. Redis is perfect for this because it supports super quick reads and writes, which is exactly what you need when dealing with session data. Let's take a look at the schema for managing sessions. We have the session table, which includes a unique identifier for the session itself, a foreign key that links the session to the specific user who's logged in, created at, timestamp marks when the session was created, expired at, indicating when the session will expire or has already expired. Using this setup, you can manage user sessions and easily log them out by deleting their session data when they log out. Now that we have explored all the databases needed for an efficient social media platform, let's move on to see what the ERD diagram looks like before ending this video. The users table stores basic users information, and each user has a corresponding profile, which stores additional details such as bio, profile picture, and location, linked by the user ID. Messages are stored in a table where each message is associated with two users, sender and receiver, via foreign keys. Posts are created by users and linked to the user table, while the friend requests table tracks requests between users, with a status to manage pending, accepted, or rejected requests. Privacy settings define what aspects of a user's profile or posts are visible to others and are linked to users via a foreign key. The sessions table stores session data for users, including login timestamps and expiration, ensuring secure access control. Also, users can comment on posts, allowing them to add one or multiple comments on posts. And each post can have multiple comments from one or more users. Reports capture any flagged content or behavior, referencing both the user and the post or message being reported. And that wraps up this step in the system design of a social media platform. We've covered the key databases that are essential to building a social media platform. Remember, if you want a deeper dive into this step, or want to explore all the other steps in detail, just head over to www.systemdesignframework.com. It's all there. And it's completely free. In the next video, we'll take things further and explore the next step in designing a social media platform. Trust me, you don't want to miss it. Hit that subscribe button and turn on notifications, so you're the first to know when it's live. See you there.